So, hello guys. Today I'm going to present the tracking people by predicting serial appearance, location, and pose in short pulp. Uh, this paper aims to track the people in the images, but it can be applied to any objects. Doesn't matter what we are tracking, as I chose people for convenience. So first of all, the contribution, unlike the previous tracking algorithms, they propose a new tracking algorithm that can make use of the history of the detected humans, see the appearances, pose information, location information to predict the future representation of each person in the video. And they propose to use a better expression of objects location as an typical Euclidean representation, and they adopt the probabilistic interpretation and compute the posterior probabilities of every detection belonging to each one of the tracklets based on the three basic attributes, means appearance, location, and pose. And they also uh, make a picture here. If you can see here, we have this person that in the second frame it disappears, although he disappears in this one, still still it it detects it after it comes out from the uh, in the searching. So the architecture is actually they are using a lot of existing architectures, which I will explain later. So in general, we can say they suppose we are tracking this person, they aggregate its appearance, pose, location information for some number of time steps, and after this aggregation, from based on the previous history of the this appearance, pose, location information, they predict the next stage of this person, and then uh, they try to associate this person with these detections using some assignment algorithms such as Hungarian algorithm. So how do they get this appearance pose location? Actually, they just use existing architecture called HMAR. HMAR is an extension to HMR, which they simply have a appearance head that predicts the 3D appearance of the detected cropped input image of the person. That's the additional information they provide. And they have also encoded to encode this 3D appearance information in this manner. And so let's go to the step-by-step process of their approach. First, they use mask RCNN to detect each person in the frame, and they collect their corresponding masks, which is useful for them. So then from those detections, they feed it to HMAR model to complete the basic representations for pose, appearance, and location on a single frame basis. And since there might be a pixel from more than one person in some detection, they further modify this HMAR model to take as additional input the pixel level mask of the person of the interest, so that we avoid the other persons. We only focus on the person of interest in that detected area. Then now they start collecting the appearance information. So as I said before, we use the mask information. So in addition, whatever they get from the appearance from HMAR model, they combine it with the visibility map, they extract it from mask LCNN, and then it becomes this kind of image in 4 dimension, and they start aggregating this appearance information using following approach. So this FA is appearance aggregation function, which takes a weighted sum of the appearance representations from the previous tracklet that they collected and the new detection. So, so this alpha is a weight. It depending on the value of the the previous appearance visibility map and the current one, it changes. So if it is both of them are 1, we use the weights, existing weights. If the previous one is 0, the new one is 1, we used 1, we make it as 1. And if the previous in previous frame we have the visibility visibility mask of 1 and the current one is 0, we use just 0. And at the start of the tracklet, they simply assign the initial single frame appearance to the tracklet like this. And they also show some visualizations of these tracklets, how they change frame by frame. And you can see it here. It slightly changes as we aggregate further and further, depending on the movements of the person of the interest. And then we go to the location. So we want to locate the person, predict the location of the person. So instead of predicting the location on Euclidean base space, they use the following space called I. They call it I, X, Y, N. X, Y is simply coming from the Euclidean space, and which is the location of the root of the person in the pixel space. And N is the nearness, defined as the Z from the Euclidean space in logarithm. And then they, the same way they did for appearance, they aggregate this location information in this tracklet, and they use this phi function for predicting the next location information from the previous aggregated information. So to do that, they simply use a simple linear regression model for predicting the next location information of the person of the interest. And this is the case for X. They do it for Y and the N separately. And for the pose, again, they use the existing model called HMMR, but they modified further. The original HMMR uses CNN model. They changed the backbone from CNN to transformer to have better representations. Then we come to the cost function. So we came all the way here. We compute the we predict the appearance, we predict the pose, we predict the location information. Now we come to the cost. So suppose we detected a person in the new frame called DI, and we want to assign it to one of the tracklets we have. So to do that, we use a conditional probabilities for each representations. So for appearance, we use Cauchy distribution to model the conditional probabilities. We try to predict this beta A parameter, and for the same way for the pose, we try to predict beta P parameter and using Cauchy distribution. But for X, Y, the location information, and to predict their to predict them, we use for X, Y, and for N separately, and we use exponential distribution, unlike the previous one. They say that this comes from empirical study that using exponential distribution works better for predicting the location information of X, Y, and nearness. And then our loss function comes as follows. We try to minimize this loss function, and they use some optimization algorithm to minimize this loss function. And after that, we perform assignment. We find the best match that has the least loss and matches with the detected person. And then we add that detected person to the track list. Then now we come to experiments. So for the experiments, they use 3 data sets: host track, MUPOTS, AVA, which capture a diverse set of sequences, including sports, casual interactions, and the movies. And as a metrics, they use IDS, the stands for identity switches. IDF1 stands for identity switches and F1 score. HOTA, the high order tracking accuracy, and MOTA, the multi-object tracking accuracy. And they do ablation study on this. They try to not use 3D appearance, and then not use 3D pose, and so on. And as you can see from the results, they're using all of this information provides better results in all metrics. And then they compare the FALP with previous methods on tracking the persons. And as we can see that there's a significant improvement in identity switches, and also for multi-object tracking, and so on. And but problem with this approach, however, as I mentioned here, they use mask CNN, so they heavily rely on the detection of humans on mask CNN, which is not the perfect model for detecting the humans in the images. So that's the main concern that they mention about this. Because even though they use the pixel level mask of the person of the interest as an additional input, this pixel level mask of the person of interest may not be so perfect because they predicted using some pre-trained model. Yeah, that's all for me.